You have done it, something on your network stopped working. Maybe your laptop says it is connected but has no internet. Maybe a device is showing a strange address that starts with 169. You restart the router, wait 30 seconds, and everything comes back to life. You have done this dozens of times. It feels like magic, but there is no magic. There's a protocol called DHCP, and once you understand exactly what it does, you will never look at your router the same way again. Every device that connects to a network needs an IP address. Without one, it cannot send or receive data. The question is, where does that address come from? In the early days of networking, administrators assigned every address by hand. That worked for 10 devices. It does not work for 10,000. DHCP, the Dynamic Host Configuration Protocol, was the solution. It automates the entire process. Your phone, your laptop, your smart TV, your printer, every single one of them gets its address from a DHCP server, usually the moment they join the network. Here's the mental model that makes everything click. Your IP address is not owned by your device. It is rented. Think of it exactly like a hotel room. The hotel is your DHCP server, the room number is your IP address, and you are the guest. When you check in, you get a room for a specific period. When that period ends, the room goes back into the pool. Other guests can use it. If you need to stay longer, you renew. That time-limited rental is called a lease, and it is the central concept in all of DHCP. A lease contains more than just an IP address. It includes the subnet mask, which tells your device which other addresses are on the local network and which require routing. It includes the default gateway, which is the address of the router that leads to the internet. It includes DNS server addresses, so your device knows where to look up domain names. It also includes the lease duration, typically 24 hours on a home router, 8 hours in an enterprise environment, and sometimes as long as 7 days on ISP equipment. All of this arrives in a single packet. Embedded inside the lease are two critical timers, T1 at 50% of the lease duration and T2 at 87.5%. Those timers drive the renewal lifecycle, which we will come back to shortly. Before any of that happens, your device needs to get its first lease. The process has 4 steps, and networking engineers remember them with the acronym DORA: discover, offer, request, acknowledge. When your device joins a network, it has no IP address at all. It cannot send a normal packet because normal packets require a source address. So it broadcasts a DHCP DISCOVR message from the special address 0.0.0.0.0 to the broadcast address 255.255.255.255. That message reaches every device on the local network, including the DHCP server. The server responds with a DHCP OFFER, proposing a specific IP address along with the full set of configuration values. Because the client still has no address, the server also uses broadcast for its reply. The client then sends a DHCP request, formally claiming the offered address. This request is also broadcast, which is deliberate. It tells any other DHCP servers on the network that their offers were not accepted. Finally, the server sends a DHCP ACK and the lease is active. The whole exchange takes well under 1 second. Now let us talk about the pool of addresses a DHCP server manages. This is called the scope. A typical home network might use the subnet 192.168.1.0/24, which gives 256 addresses. The server does not hand out all of them. The network address at the bottom and the broadcast address at the top are reserved. The administrator typically excludes a range for devices that need predictable addresses: the router itself, printers, access points, servers. The remaining addresses form the pool. Within the pool, the administrator can create reservations, which are permanent bindings between a device's MAC address and a specific IP. A reserved device always gets the same address, but unlike a static IP, it still goes through the full DHCP handshake. This is the right way to give a device a permanent address because the router hands out the gateway and DNS settings at the same time, keeping everything consistent. Once a device has a lease, it does not just hold it forever. The 2 timers built into every lease drive a predictable life cycle. During the active phase from 0 to T1, the device uses its IP address normally and there is no DHCP traffic on the network at all. When T1 arrives at 50% of the lease duration, the device sends a unicast DHCP request directly to the original server that issued the lease, asking to renew. If the server replies with an acknowledgement, the lease is extended from that moment and the full duration resets. The device goes back into its active phase with a fresh lease. If the server does not respond by the time T2 arrives, at 87.5% of the lease duration, the device enters the rebinding phase. It now broadcasts a DHCP request to any available DHCP server on the network. Any server can respond and extend the lease. If nothing responds by the time the lease fully expires, the device releases its address and starts the DORA process from the beginning. There may be a brief connectivity gap during that renegotiation, but on a healthy network it is usually invisible to the user. Things do not always go smoothly. There are 4 failure modes worth knowing. The first is APIPA, which stands for Automatic Private IP Addressing. If a device sends 4 DHCP DICOVER messages and receives no response, Windows and macOS automatically assign an address in the 169.254.0.0/16 range. This is a local link address only. The device can talk to other APIPA devices on the same segment, but it has no gateway and no internet access. If you ever see a 169 address, the DHCP server is unreachable. The second failure mode is a rogue DHCP server. If a misconfigured device on your network starts responding to Discover messages before your real server does, clients will accept the fake offers. The rogue server might hand out a wrong gateway, redirecting all your traffic. The enterprise solution is DHCP snooping, a switch feature that only allows DHCP replies from trusted ports. The third is an IP address conflict, which happens when a device is given a static IP inside the DHCP pool range. Two devices end up sharing the same address and both become unreliable. The fix is always to either use reservations or assign static addresses outside the pool range. The fourth failure mode is lease exhaustion. If every address in the scope is already leased, new devices get no offer and fall back to APIPA. The fix is to expand the scope, shorten the lease duration so addresses return to the pool faster, or segment the network with VLANs. DHCP delivers more than just an IP address. The protocol includes a rich options system where each piece of configuration data has a numeric code. Option 1 is the subnet mask. Option 3 is the default gateway. Option 6 is the list of DNS servers. Option 12 carries the hostname. Option 42 specifies NTP servers for time synchronization. Option 43 is vendor-specific information used in enterprise environments to tell wireless access points the address of their controller. Option 66 points diskless devices to a TFTP server for PXE network boot. All of this configuration flows to the client in a single DHCP ACK. One exchange and the device knows everything it needs to participate on the network. In larger environments where a single DHCP server serves multiple subnets, a relay agent running on the router converts client broadcasts into unicast packets and forwards them to the central server. So one server can serve an entire enterprise without a DHCP server on every floor. Now we can answer the original question precisely. When you restart your router, the DHCP server process terminates. Any lease state held only in RAM is gone. The devices still on your network continue holding their old IP addresses in memory, but the gateway is unreachable. When the router finishes booting, the DHCP server starts fresh. Devices that maintain their connection may silently retain their lease if the router reloads it from persistent storage. Devices that drop their connection broadcast a new Discover. In most cases, the router offers the same address back because it is still free, and the full DHCP ACK reconfigures the gateway and DNS settings from scratch. That reconfiguration is the key. If the problem was a stale DNS cache, a misconfigured gateway entry, or a lease that had expired mid-session, the fresh DHCP ACK fixes it. Beyond DHCP, restarting the router also clears the NAT connection tracking table, dropping any half-open TCP sessions that were keeping connections in a broken state, and triggers a fresh WAN authentication with the ISP. That combination of a clean DHCP reconfiguration, a cleared NAT table, and a fresh ISP session is what makes the router restart such a reliable fix for so many different-looking problems. That is DHCP, a lease-based protocol that assigns IP addresses, gateways, DNS servers, and dozens of other options automatically, renews them on a predictable schedule, and resets cleanly when the server restarts. Thanks for watching.